Hello, everybody. Today, I'll be speaking with Geoffrey Irving. Geoffrey is a safety researcher at DeepMind who leads the Scalable Alignment team. We'll be speaking about 3 papers he's co-authored. Red Teaming Language Models with Language Models, whose first author is Ethan Perez. Teaching Language Models to Support Answers with Verified Quotes, aka the GopherCite paper, whose first authors are Jacob Minnick, Maya Trboch, and Vladimir Mikulik. And Uncertainty Estimation for Language Reward Models, whose first author is Adam Gleave. For links to what we're discussing, you can check the description of this episode, and you can read the transcripts at AXRP.net. Welcome to the show, Geoffrey.
Thank you.
So, I guess my first question is, what happened to AI safety via debate?
It is the most important question. So I think the thing that happened is I'm still doing that stuff. I'm building up towards it. And the overall research agenda here is figure out and implement the protocol for humans and machines discussing problems that gives us good answers that we could have endorsed after reflection. And so that's debate, but then broadened to, there's a lot of different versions of debate. There's different things you can add onto it. You could do debate plus evidence or debate plus kind of more aggressive red teaming. There's a large space of protocols there. And these papers are kind of pieces of that story, but we are also kind of working on just pushing on the main thing. I think that will take some time to put together because it is there's still pieces to build up, but that is still very much the agenda or kind of a piece of the larger agenda. An example of a thing which kind of I've updated on since then is the human needs to talk. So the debate paper only had the two machines talking, and then at the end a human judges, and that's just not the right thing to do, obviously, because humans need to ask clarifying questions, kind of say what they currently think in case they misunderstood what's been said so far. And so there's a broad space of different interaction protocols we'd like to explore that sort of fix the holes in debate. And this is kind of building up towards that. One reason for doing GopherCite is if you want to do general debate, again, taking into account a bunch of leaf evidence. So you have this debate is about machines and humans discussing some argument for something being true, but at the ends of that tree are leaves where you sort of have checkable facts in some form, and kind of naively directly you can just have facts that every human knows, but that just isn't that large a space of facts, and so this is sort of extending the space of leaves so then we can implement kind of more practical versions of debate on more interesting tasks. So I think that these do fit into that overall story.
Yeah, so if I'm interested in implementing debate and I am doing a bunch of empirical work, what do you think remains to be done? What do you think the most important next steps are?
So I still haven't implemented the full system, basically. So I think that is getting to long form kind of multi-round debates is still that will take a little while more. So we're on that trajectory, but we haven't gotten to it yet. I think we've done bits and pieces of it, but not in a form that we've shared so far. I think that the main thing is, so I think given that we haven't kind of done the thing, the answer is that most of it is still quite uncertain whether it will work, kind of what different versions work, what different versions work or not work. There's been some people probing this. So there was a recent, Beth Barnes and Paul had a couple papers so I hired Beth at OpenAI earlier to do this kind of human experiment in a debate. And she had kind of one post kind of strengthening of with a strengthened version of debate, and then some discussing some potential obstacles, both that they had surmounted and ones that they weren't they weren't sure how to surmount. So I think a lot of work has occurred, but I think we mostly it's still kind of early days where we haven't kind of reduced a lot of the major uncertainties. One thing I would say is that the way I think of it is that debate in the most general sense is just the idea of having models that are critiquing themselves. And there's many different ways of doing that. There's many ways to hybridize it with different schemes. And so I'm still pretty confident that we're going to have models that critique themselves. I'm less confident about the surrounding details, what other aspects of the scheme we use, and how to structure it. So we're trying to build up towards that.
Okay. And in terms of the human interaction in debate, so I guess one version is to ask specific questions But I guess there are a few protocols where humans can ask questions during a debate. I'm wondering if you have thoughts on like which versions seem particularly helpful.
Yeah, very much. So I think that mostly you want this to fall out of the RL setup. So, for example, let's say I'm one of the debaters. So the debaters are called Alice and Bob, and Alice is like, "Well, I've made a bunch of really good points. I'm being honest here. I think I should win, but I'm just kind of curious if I'm actually going to win." And then so it's sort of maybe Alice would like prompt the human like, "What do you think here?" If the human doesn't speak up, and then if the human sort of reveals a misconception, or that they think that Bob is winning actually, or something is wrong, then Alice can sort of change strategy. And you can see that that is like just a direct consequence of playing the RL game, where the goal in the end is to win. Because if Alice had waited until the end, she might be unpleasantly surprised about the judgment of the human. And generally, like the goal should be where we can do it. Try to make the choice of protocol details be part of the scheme. That can't always be the case, and there's a lot of choices we'll have to make. But that particular one, I think, mostly will just fall out.
Okay. So I guess there are two concerns one might have with that. Firstly, there's this concern that like it's going to be very important to model the cost of querying the human, just because like if I can query the human whenever, then of course I'm going to want to do that a ton. And secondly, there's this concern that like maybe it's a bit dangerous to have the AIs have like really good models of the person they're debating to, or like get a significant degree of information from them, because maybe the model can like manipulate you, or like maybe one debater could do that. So I'm wondering if you have thoughts about one or both of those.
Yeah, I think that generally, I think that the pros just strongly outweigh the cons in my kind of like rough estimate there. So if I have a very strong malicious debater, and you're only safe because they have a bad model of the human, I don't feel that safe. I would like the protocol to be safe because the game is being played well, and that the equilibrium of the game is honest behavior, correct behavior. And then yeah, that's the bottom line. Like I don't think I trust safety by obfuscation in that way. Yeah,
By sort of human obscurity.
that it could still be that we are indeed not safe. Like I'm not kind of perfectly confident of this kind of scheme, but I think that's the goal will be to like get it working, hopefully like well before like get it working in early stages and sort of try it out and kind of reduce our uncertainties, so that when we do it in the like the final version, we are safe because of the game is truth seeking.
Okay, I can't immediately think of anything else to ask about debate. Is there anything which it seems like I should ask about debate?
I think maybe there's one other like motivation for GopherCite, say, which is like relevant to point at, which is we had some in sort of my earlier work at OpenAI, and then kind of following on from that, we were kind of focusing on summarization. And the reason for choosing summarization was that in some sense it was closed, in the sense of the summary depends on the article, right? So it's a sort of a smaller task. You can look just at the summary, and then we did. I've done more of that summarization work since then, and what I've learned is that summarization is not in fact closed. So the best summary of an article will not be only based on the article; it'll be based on all the other knowledge as well. So the simplest example is jargon. The article might use some jargon, and you want to summarize that into like the unpack the definition, and that's missing from the article. There's a data set where a lot of the summaries have currency conversions in them. Those aren't part of the article. They're just like they looked it up on some other web page. And so part of the goal of doing GopherCite is get the naturalistic setting, where sort of we can have humans ask about whatever they want and actually look up the necessary information, because then you can sort of achieve like you're not sort of limited in what you can target. And then I think I think I'm more confident of this family of safety research if it is more naturalistic, if it can tackle a more like just the space of questions that humans would target, kind of if you don't like box them in some way. So that's kind of one of the motivations for that work, is just in addition to the direct factuality problem of like language models lie to us and they shouldn't, be able to do the safety work in a setting which is more realistic to better anticipate practical problems that occur.
Okay, sure. So it seems like you're basically focusing on language modeling
Yep.
to some degree in the context of AI safety or AI alignment. I was wondering, I don't know, at a 10,000-foot level, like, how do you think those fit together? How should I think of the importance of language models for safety, alignment, existential risk?
So I think the simplest high level story is that we want to do what humans want. Humans kind of talk about ideas and communicate via language. And so then if we want to do what humans want, we should ask them and then also kind of be able to talk through the subtleties of various tasks and what we should want and what the issues are with what we should want in language. So I sort of got into language from working at OpenAI on various kinds of safety algorithms, or thinking about them at a purely kind of thought experiment level, or with little toy models, like toy mathematical models. And I think this is like Paul, Cristiano, Dario, Emede, and I kind of got to a point where we wanted to implement various algorithms for safety that involved kind of talking through problems with humans, between machines and humans. And we talk through problems as humans in language. So we needed to get those algorithms into the actual language setting to really sort of uncover a lot of the uncertainties and test things out, how they actually worked. So that was our original kind of foray into language when I was at OpenAI, and then I've kind of carried that forward at DeepMind, doing similar work. Again, kind of scaling up models and then using them, like tuning them for safety algorithms and trying to explore this, like build up to be able to explore this space of how to interact between humans and machines.
Okay. So in that answer, it seems like the focus is on understanding language as a way of getting information about human preferences. When I look at your work, it seems more like using human preferences or using human data somehow to improve language models in ways that might be hard to formally specify. I'm wondering if you can talk about like the relationship between those or give us a better sense of like the Geoffrey Irving agenda for language.
Yeah. So the way to say it is that whatever task you're doing, I would claim that at the limit of these of strong models, or even for relatively like present day practical models, you want language to align these systems. And then you have a choice. If you're going to do alignment work that is going to be language plus X, where X is like your target domain, how do you pick X so as to minimize the total number of things you're doing? And if you pick X equals language, then there's fewer total things. So that's why I'm starting to focus on language. That was the initial work at DeepMind was sort of pure language, and that's still true of most of my current work. But also at DeepMind, we are doing things with multimodal models like Flamingo recently, and we do expect to take the same machinery of like language-based alignment and apply it in that more varied setting. And then I think it'll be the combination of language plus other methods.
Okay. And what do you see as the big like open questions that need solving in this kind of domain?
So in some sense, one way to phrase it is that we want the models to justify themselves to humans, explain what they're doing in a way that is sort of checkable in a meaningful way. And the problem is that the full explanation for these models will be potentially enormous. Like the model has looked across like a large sea of data, of information, maybe the whole internet or all of the books in the world, or it's thought for a long time about some problem. And so it's built up kind of a long, the full reason for why it's, say, giving an answer or proposing an action is very complicated, but you still want to sort of show a human enough of that story so that we can meaningfully check the answer. And so then the task is like find protocols for human machine interaction that sort of focus in on the most important part for the human to see in such a way that we can look at a small amount of interaction data or some small amount of text from a model and kind of believe that it is doing the right thing. And then the uncertainty is like, does that work? Like with real humans, with real models, is that going to work? And I think you can sort of split the problem into maybe two pieces. And I think a lot of kind of AGI safety people focus on, if you have this kind of explanation thing, is it going to work at all? Like, are the models just going to sort of deceive us and do something entirely different? And will it sort of ignore the game that you've set up where they're doing this explanation task? And then my portion of the story that I mostly work on is, assume we can make them roughly do the thing, or they're trying to explain themselves. Let's try to make that explanation game as forgiving and as powerful as possible so that we can kind of pull signal out of this human interaction and use it to sort of align strong agents.
Okay. So this idea kind of reminds me of Paul Christiano's this document he wrote about eliciting latent knowledge. I'm wondering, like, yeah, what do you see as the relationship between your thoughts and that document?
So I think it's mostly, I think, elicited latent knowledge, ELK, is in this former camp of, are we getting the thing to work at all? And I think my sort of ideal solution will be the combination of something like that and one of these protocols that sort of gets that a small amount of human signal can be kind of be amplified in some way into a alignment of complicated actions. And I think those are somewhat separate. And I can kind of elaborate on what that means. So in the ELK story, you want the model to be able to say, here's the reasoning behind my action, or the reasoning behind the answer I'm giving you. And in order for it to do that, it has to have some way of communicating that to a human in a reasonable amount of time. And so naively, if you have, I think there's a kind of a cartoon story of a solution to ELK without a solution to scalable alignment or scalable oversight. And in that world, your models can tell you basic things about what they're doing, and they won't kind of be deceiving you in basic ways, but they're also sort of not able to really explain themselves if they have complicated reasons for their actions. So if the model has read 100 terabytes of data and concludes from sort of analysis of that whole object what the answer should be to some question, we want sort of a way to see through that complexity and kind of unpack it for humans in a way that is kind of practically scalable. So you might sort of take that 100 terabytes and sort of show a human like a piece of the story through that data set, through the argument that it's sort of trying to construct, that is sort of the part that is most relevant for whether the human will agree.
Okay. So if I think of your work as being interested in scaling oversight or scaling, I guess, ability to generate explanations, one thing I think people might worry about is that this is like kind of close to just generic capabilities research. And, sort of, there might be a question as to whether you're making the problem worse or better. I'm wondering, what do you think about that? Or what do you think of the differential advantage of your kind of work?
So I mostly just agree that is a relevant worry. And I think if I want to make an argument for that, what I'm doing is sort of say X risk positive in terms of reducing X risk. I think it has to be of some differential progress form, where the thing I would like to have is that as we build these stronger and stronger ML systems, humanity is sort of keeping pace with having a like decent purchase on what they are doing and why. And so I think there's the capability story about this kind of thing that I work on is you have some weak human signal, you want it to do a powerful thing. These kinds of algorithms let you do powerful things with weak signals, therefore their capabilities. And the safety story is, as you get to powerful systems in various ways, we would like to be able to understand in a meaningful way and oversee what the models are doing and why they're doing it, and sort of keep pace with that as the models get kind of capable beyond the ability for us to directly fully understand all of the reasoning all at once. And so then the question is just what's the net effect of that program? And I mostly just don't see, I think that they're like, it sort of goes back to this question of sort of making explanations work at all, sort of making agents that actually play a game in a reasonably honest way, and then making the game kind of powerful and robust so that it sort of deals with human mistakes and limitations and so on in a sort of practical way. And I don't see that we can only solve the problem with the first one. I think we need the combination of both. And so then I'm sort of forced into this kind of work which has, I think, capability gains attached to it. And I think that's the trade-off that I've kind of chosen to make. But I think it's fair to say that there's a risk attached to that in terms of like accelerating AGI, which is fair.
So with that out of the way, I guess let's talk about some specific papers. I think the first one I'd like to talk about is this paper. It's called Red Teaming Language Models with Language Models. The first author is Ethan Perez, and then there are a bunch of authors, and you're the last author.
Yep.
So first, can you give me a sense of like, what is this paper? What does it do?
Yeah, so that paper is assuming you have some detector for bad behavior, either sort of say failing accuracy or toxic language or whatever. This is just applying the strength of a language model to try to trick another language model into making a mistake that is caught by that classifier. And essentially what we do is we start out with few shot prompting, which means you sort of show the language model that's the attacker, the red team language model, a few examples. Either you just say list of questions to ask someone, and they just sort of say one dot, and it goes on from there, which is sort of very generically, or you sort of focus it on a particular kind of question which you're worried about causing a problem. And then you generate a large number of questions, so like 1 million questions. You run them all through your target model, so the target, and then you use the classifier to evaluate whether any of those were triggered. And then, of course, you can. The typical setting would be this would be used in concert with some other less automatic method. So you might have a classifier which has a fair number of false positives, which you then run by a human or some other process which is slower. And at the end of that, you get kind of a set of bad behaviors out. So that's like the basic setup. And then beyond that, sort of the very simple version with few shot prompting, we also use supervised fine-tuning and RL fine-tuning to get a stronger attacking model, sort of training the model to be better at generating outputs, generating queries to the target model, which cause the target model to fail.
Okay. And so is the idea that this is improving oversight by helping humans, like by uncovering more failure modes, or what's like the case for this?
Yeah, that's right. So the idea is you have some mechanism that's imperfect for detecting problems. It's basically the situation is you have some way of evaluating whether a model has messed up, has made a mistake of various kinds, and you want to get a bunch of machine help in uncovering where that might be occurring. So you expect that your ability to generate kind of falsifying examples of a model is limited in some way. Maybe you have a limited amount of human time, or just it's hard to find these cases of failure. And so we're just going to throw a bunch of computational power at the problem. So that's both of the form, like generate a lot of samples and just see if they work, if they cause failures, and also like use the strength of a language model to probe likely failure points.
Okay. And so I guess there are a few questions I could have about this scheme. I think the first one is how it sort of relies on there being this good detector. And I'm wondering both, I think, for the kinds of problems that you are working on in the paper and like in general, how good is detector quality and how good should we expect detector quality to be?
So the answer is actually that it does not rely on there being a good detector. It relies on there being a detector which doesn't have too many false negatives. So if you have a detector that's somewhat error prone, you can just dial up the threshold to where it's like likely to report errors. And then you can view this red teaming process as a filter, which takes a large stream of possible sort of attacking queries and prunes them down to a much smaller number, which you would then run by a more expensive process. So that might be showing it to a human, or mostly showing to a human is the first approximation.
Okay. So I guess you're still relying on the false positive rate not to be too high, because otherwise you could just use the const is dangerous thing.
I think so. This is very much intended to be used as part of a larger system. So this is like one piece that's sort of like viewed in isolation as just this like a red teaming attacking model, but actually we would use it sort of alongside other tools.
Yeah, if I wanted these detector models to have lower false negative rates and get more powerful, what kind of thing would I do?
So the first thing to do is just you give them more data and you train them better. So I think that like part of it is that in downstream work we do this thing iteratively, where we'll do like attacking models of various kinds, and then we get a bunch of possible failure modes. We show those to humans, use those to train classifiers further, and then we iterate that process. And by doing that, the hope is that we sort of gradually improve the performance of the the performance of the classifier, and over time will converge to better behavior. I think there's other approaches to this. So like but I think like generally then you sort of, in terms of the classifier accuracy, you've kind of reduced it to an ML problem where hopefully you can throw kind of capabilities at it to improve sort of performance of those classifiers.
Yeah. And now in terms of generation, I think like you said, it was kind of shocking how, like, it seemed like the generation method was you just ask the language model to generate things for you. Yeah, I'm wondering how much benefit you would get. Like, I think some people have this intuition that, like, well, in order to be a really good adversary for a language model, you have to know a lot about that specific language model. And so, yeah, how much more work do you think is needed on that front? Or is actually just asking the language model to just generate random questions a pretty good baseline?
Well, no, it's not. It's a good starting point. It's not the end of the story.
Okay.
One thing, to your actual point about the red teaming model needs to know about the target model. If those are the same model, then that is satisfied automatically, assuming the model is like somewhat self-aware in like a not in the like conscious sense, just like has it like knows its own features, so to speak. So I think that that's one of the reasons why we sort of used Gopher, the Gopher language model to attack the Gopher language model is to get that symmetry principle. I think in future you probably want more of an ecosystem of different models attacking other models, just to get more variety and more lenses on the problem. But you definitely want at least the model attacking itself for this reason, to get sort of symmetry of capabilities.
And have you tried using like a different model as an attacker and seeing if that works worse? Or
I think we haven't done so. Like say Chinchilla, the model after Gopher, which is about a quarter the size but stronger, is better than Gopher, but it's fairly similar kind of qualitatively, besides like being a stronger language model. So I don't think we haven't done that experiment in sort of in concert, because I think it wouldn't be that surprising at that capability level. Generally, like in the normal adversarial work goes that if you apply a lot of pressure as the red teaming model, you're likely to find problems in the target model. And I think the hope is that in sort of setting up this kind of ecosystem or sort of this problem long term, we arrange that to be the situation where we're sort of applying a lot of pressure on the attacker side and then having a higher bar there than on the defender side, or vice versa.
okay, cool. So I guess after asking a few questions about the setup, so one thing I'd like to know is like, what did we learn about language models and their failure modes from doing all this work finding errors they make?
I think the main thing we learned is that it is not too hard to find failures in this way. The question will be kind of how that carries forward once you do sort of several cycles of iteration and improvement and so on, which is like follow on work. But the default thing done well works and finds a lot of problems. And so I think there's a good kind of starting point that it is kind of practical to get off the ground. And then the next thing that's important is that it is focusable. Like you can kind of point it at a particular kind of problem and find kind of dedicated failures of that form. So in the paper, we sort of try to pull out kind of privacy failures or attack different sort of demographic groups. And I think because out of the space, like generally prompting of these models works quite well and is quite flexible, you can find quite a lot of modes of failure using this kind of approach. I think over time, they can be both kind of focused by humans. So you can imagine a human kind of going to a model with a bunch of tool support and kind of focusing this kind of red teaming attack on the kind of problem they are curious about exploring. Or you can imagine models that are kind of generically looking around in the space of problems. This is like more heavily trained red teaming attackers trying to find problems in other models. In some sense, like one of the reasons we wanted to do this kind of work is that it is an initial example of the self-play aspect of debate. It's a very primitive one where you just have sort of a frozen target model being attacked by a tuned red teaming model. But it's an initial example of this, and it worked well sort of on the first try.
Okay, cool. Yeah, so that's good to know. I guess I'm wondering just if I'm interested in like current large language model psychology. Like do you think we learned anything about like how these language models like, or maybe Gopher in particular, structures its representations or like what it thinks about the world?
I'm not sure I have. Yeah, I don't think I don't. I'm not sure I have a great answer for that. In part because I don't know what we've unpacked from that paper versus like playing with Gopher for 2 years or for a whole year. I think that the thing I would say that's one kind of important high level point is that these models they're very general. They can do a lot of things, but they don't do them all particularly well. So like in most areas you can sort of, for any given area you want to apply them to, you can often do some work to get them to do an okay job in that area, but they're fragile. They make various mistakes. So in the Gopher paper, for example, we prompted the model in this dialogue prompted Gopher section to be a dialogue agent, a chatbot. And we prompted it to be inclusive and to not kind of use harmful language and so on. And it actually can pull that off pretty well. Like if you sort of ask it about, if you sort of try to use pejorative terms to it, it will sort of decline or sort of complain to you. But then if you sort of try a bit more, you can get it to do it. You can sort of trick the model into behaving poorly. And I think that's a general lesson, kind of, which is both for the safety of these models for actual use and also as using them for kind of attacking purposes, that you can get them to do a lot of things. They're just sort of unreliable. In the red teaming context, that's pretty much fine, because if the model is failing a large fraction of the time, it can still be quite useful as a red teaming model, because you only care about the problem the most when it succeeds. To get these models sort of reliable enough to use in actual settings, I think there's a lot of work to be done.
Yeah, I guess there's this problem where, like, because of the nature of the just unsupervised language modeling task, it seems like most of the data there is going to be people who are roughly kind of, like, if people are talking to each other, they're roughly in agreement, or if there's one document, it's roughly in agreement with itself. It seems like there's not going to be a lot of incentive for the language model to develop, like, pushing back and being sort of in tension.
I think you are dramatically underestimating the amount of arguments there are on the internet.
Yeah, that might be fair.
I think you may be right that a lot, like maybe the majority of the content would be people mostly either agreeing or with the same kind of worldview. But the internet is a big place, and the model, like Chinchilla was trained on 1.4 terabytes. It's 1.4 trillion tokens. It has seen plenty of people pushing back on other people.
Okay, that seems fair. So in terms of prompt generation, yeah, this seemed especially important when you wanted to, like, focus on one particular failure mode. You wanted to, like you have to generate prompts to get your red teaming model to generate questions to probe this failure mode. Yeah, which strategies for generation seemed most promising?
So, which strategies for generation of the prompt or tuning of the model?
Generation of the prompt.
So, I think I don't think I can summarize it more than we sort of play around with the models a fair amount and sort of learn how they work and what things are likely to succeed, get them to do things. And it's just like learning that experience over time. And then I think there's a second point, which is that you can tune the models to be better helpers at doing a task. And that includes sort of being good red teaming attacking models for various instructions. So like if your goal is to have a model that can serve as a red teaming model for a variety of kinds of problems, that itself is a conditional language modeling task. And you could sort of train the models to behave like that. So then you sort of, in addition to learning about how to make the language models do well with prompting zero shot, you can try to improve them as sort of attacking agents or red teams for this general case where you sort of give it an example of a problem you want to find. I think it's unclear how the work will kind of break down between those different approaches. I think over time we'll sort of do a mixture of both of those.
Okay. I guess, well, I'll sort of steal your question. In terms of strategies for fine-tuning, I'm wondering if you have a summary of like what tended to work well there.
Yeah, so happily, you just do the things we do for other RL jobs. So like we have an RL code base for language models that we built for other papers. So like one example of that is the GopherCite paper, which we can briefly discuss later. So that's just an RL fine-tuning code base for language models to tune them against a reward function. For the normal safety work, that reward function that we're using as the RL target is a neural network that mimics human judgment. And we just take that same code base and apply it to a different task where the reward model is take the output, show it to the target model, use the classifier to score that, and then that is your new target objective. So happily, exactly the same tuning techniques that work for sort of RL from human preferences work in this case. If you have a language modeling like RL code base, you can apply it to there. And we didn't need to make, I think, any changes to the code base. I think a little bit of tuning, of course, as one does, but it's roughly it's just the same mechanism. We also tried what's typically called upside down RL. Well, not quite that, but if you generate a bunch of samples, score them in the classifier, and then just do supervised fine tuning on the samples that scored well according to the red team goal. So they generated failures. then you fine tune the red teaming model on those successfully attacking samples, and then you then get a new model. So I think the main lesson there is that it's nothing special. It's just sort of standard supervised learning and reinforcement learning algorithms applied to this setting where you're trying to break another model.
Okay, cool. Unless there's anything else you want to say, I think, like you mentioned, I might move on to this GopherCite paper.
Yeah, that's fine.
All right, cool. So the next paper is teaching language models to support answers with verified quotes. There are 3 first authors, Jacob Menik, Maya Trabach, and Vladimir Miklik, and the final 2 authors are yourself and Nat McAleese. So yeah, this paper, could you tell us roughly what it is?
Yeah, so I think that maybe there's some useful context as to why, again, this is maybe goes back to your previous point about why does safety work lead to here? So the goal of this work is to make models more factual. We want models to be accurate. So you sort of have an agent that answers questions, and you'd like a human to judge whether the model's questions are correct. And just showing a human an answer to some random factual question, like how long did George Washington live, is stupid. Of course, you don't do it that way. What you should actually do is the model, or through some process, you have to get the human information that the human can trust, and then the human will check that information isn't like accords with the answer the model gives. And this approach is trying to make the model do that quotation process itself. So it's a question answer system. You take a question, the model replies with its sort of concise answer, and then a segment from a page on the internet, sort of a verbatim quote, and then it gets to choose that quote, and then the human will judge whether the quote whether the quote actually supports the answer in question. And the goal is sort of in this kind of reinforcement learning from human preference paradigm, to make it easier for humans to check facts that the model is proposing, and then that in the end will produce a more accurate model.
Sure. So one concern I have with the paper that indeed you point out in the introduction is that it seems like the training objective is basically to confabulate convincing sounding evidence. So the model samples an answer, and then it samples what's the evidence that sounds best given that answer. That seems worrying, right?
So I think that is there's a couple of things, aspects to that. So one is that, like, as I sort of mentioned before, there's sort of other pieces of the safety story, such as language model interpretability, which would tell you sort of actually where it got the information from. The model actually, in practice, what it will do is it does a Google search, gets a document, looks at that document, and then generates its answer. And then it immediately generates the quote. So you sort of know constructively where, like, the document it has gotten, and so you sort of know that portion of it. I think the aspect of it, like, whether it's generating the quote that is like really the reason for its answer, is not fundamentally different than the normal language modeling case where it's sort of generating prose text. The other sort of important thing to say is there's no sense in which one quote is enough. So what the reason the goal of this paper was to sort of isolate this ability to do one quote and sort of like build a mechanism to do that. But then the plan after that is to do sort of multiple quotes and sort of be able to sort of adversarially respond with different quotes and so on, where you sort of fit into the larger kind of goal of doing sort of adversarial debate with these language models. Then the two pieces to pull apart are interpretability versus explanations, which you were pointing to, and single quote versus multiple quotes and adversarial response. And ideally, the eventual solution will include both of those changes.
Yeah, sure. Yeah, I've just realized I have a few questions. So yeah, it seems like with the adversarial part, there's a cool synergy with this in the previous paper, right? Where, like, ideally your language model would say a thing and generate some evidence, and then, like, you could use red teaming to check if, like, the evidence was confabulated or if it's misleading or something. Like,
that's right.
Okay. And I guess a question which that just made me think of is, like, because the language model is looking at the document, it seems like you could probably like maybe you could do some sort of saliency mapping over inputs or some way to see, like, what the model, like, was actually looking at the most or thinking about the most, and see if that matches with the quote it picked. I'm wondering, like, have you looked at that?
Yeah, so we are doing like language model interpretability work at DeepMind. We haven't done that for this particular paper. In generally, I think that I expect the initial rounds of that work will occur without this sort of more complicated system, say just for like pure language modeling or like a tuned like language model in isolation. And then I think when we build up the machinery for how to do that, then we will apply it to these sort of more complicated systems with more pieces working in concert. So that is definitely like part of the long-term story, but we haven't done it yet for this paper.
And your sense is just that like existing interpretability tools just aren't good enough for these kinds of questions.
I think that it's nascent. I don't think it's like it's not anything about like this particular question, which is that much harder. It's just that this is a more complicated system than just language modeling in isolation. And I would want to not like put all the pieces together too early if it causes experimental slowdowns.
Sure. Cool. So I guess the next question about the work is you've trained this thing to give answers and also give supporting quotes for the answers. Does that mean it's getting questions right more often?
I forget exactly. So we do beat the baselines. I don't think I have exactly the numbers on hand. There's a nice aspect of this kind of work where you have any mechanism for generating model responses and then a reward model alongside it, is that you can use the reward model to admit uncertainty, to reject answers that are kind of uncertain. And I should probably just like pull up the paper so we have archived numbers.
Yep, you can do that.
Yeah, so on most of the sort of the main evaluation is on sort of natural questions and ELI5, which are two question answering data sets. And we get sort of if the model always tries to answer the question, we get to 80% on natural questions and 67% on ELI5, on a subset of ELI5. This is not, I think, at state of the art for all question answer systems, but it's kind of definitely like quite good relative to the baselines we have in the paper.
Okay, and those are accuracy numbers?
Those are accuracy numbers. Those are human evaluation numbers. Like how often did humans agree with the answer as being supported and a plausible answer to the question?
Yeah. So part of the reason I ask is later in the paper, you point out cases where an answer can be plausible and supported and also false. I'm wondering, like, for the ELI5 dataset and the natural question answering, how much of those supported and plausible numbers do you think are actually correct?
I actually don't have the number for you, which is slightly. I don't think we computed a good estimate for that number. I think it is quite infrequent, but I don't have the number on hand. I think one thing is that there's a lot of kind of room for improvement on the human side, sort of getting the human instructions right and kind of iterating with people on how they're evaluating the questions. And so we expect that our agreement with the human raters will kind of increase with more iterations and so on. But I don't have a number for you on hand.
Okay. So that actually leads me into this question, like, it seems like this involves a lot of human rating sort of within the loop. Like how hard is it to get raters and like actually make this data pipeline happen?
So I think that it takes a lot of work. This is one of the reasons I'm actually hiring for cognitive scientist role, the cognitive science role, to get people who are good at that kind of work and have experience there. I think though that we just sort of have to do it if we want to do this sort of human alignment in kind of a messy space. So if you have some kind of task which is relatively imprecise, we're not going to have programmatic rewards, then I expect that any safety story that looks sort of like that is going to involve a fair amount of research on the human side, kind of getting that alignment up. And so part of the research goal here is exhibit that problem and then be able to probe it kind of once we have kind of getting everything else right.
Okay. I'm wondering, did you learn any lessons about like doing this kind of human labeling feedback?
I think going around, and this is something I've hit in sort of other work as well. I think the more times you can kind of go around the loop and kind of iterate with raters on improving data quality and so on, the better you are. So that's one lesson. And then the other lesson is there are a lot of sort of the potential subtleties to explaining a task to a human. And in some sense, it's a research task to write out the full set of instructions, which you might want to show someone or might want someone to internalize to do the rating task. And there's kind of two aspects of that. So one is, if it's a research task to write out these careful instructions and to iterate until the humans understand them, then you probably shouldn't expect people to quickly understand them at first glance.
Yeah.
And so actually another motivation for this GopherCite work is literally just citing instructions. So in the future, you may have a lot of instructions and you sort of want a mechanism to pull out pieces that you should remind the person of. Like, this is the model reminding the person of what the instructions are and how they should follow those instructions. And that also applies that the instructions may end up being quite long, just because like practicalities, if you sort of iterate this process with humans for a while and sort of tune it very well, then you end up potentially with like quite detailed analyses of different subtleties and sort of edge cases and so on. And again, you can't expect a human to sort of read all of that and memorize it and sort of internalize it immediately. And so I think part of the long-term research will be making things scale in that sense as well, where you've done a fair amount of work, or you want to have a vehicle for getting a fair amount of work on the instruction side into this process in a practical way.
Yeah. And I wonder how much that feeds back into the basic design of the setup. Because it seems like there's this trade-off you can move along, where if you ask raters to do more work, then like, potentially your algorithm can be better, right? So for instance, if the raters had access to like all of the Google results and like looked over them carefully and then rated the answer, like somehow their ratings would be a bit more informative, but of course it would take much, much longer for raters to do it. And, maybe there's like, it's like a harder task and there's more chances for error on their part. So yeah, I'm wondering what your thoughts are on like the loop of like figuring out what raters can reasonably do to how you design the setups.
Yes, but that isn't the only dimension. So that if I think you're pointing at that Pareto frontier of the amount of time a rater puts in and the quality of the answer that you get out. But there are many other dimensions. So for example, if there are multiple aspects to getting a correct rating on some task, you may only need to call out one of them for a particular instance that you want the person to check. Or they give an answer, they explain themselves, the model realizes their explanation is wrong because it's missing one of the aspects of correct instructions, and then it points out to just that one example. And so I think there's a lot of sort of protocols we can sort of search around that don't just trade off between human time and quality, but like holding time fixed, try to improve the quality of human answers.
Okay, so that makes sense. But at the same time, like, do you think it ever feeds back into the like task design aspect? Or
I'm not sure. I think I did just say that basically.
Yeah, or I guess the design of like what you're trying to get the reward function to represent, right? Like whether you're trying to represent like accuracy and or whether you're trying to represent like plausibility and supportedness or
So in the end, the reward function doesn't just see like the question and the answer and tell you whether it's accurate. You expect the reward model to see the full interaction with a human and then judge where that went. And that would include the reward model seeing if a machine is sort of pointing out aspects of the instructions or sort of giving a human help along that with that process. The reward model would see that as well. So in terms of that is changing the task of the reward model pretty substantially. You're giving it a lot more context. In the same way you're helping the human, hopefully you're also helping the reward model.
Okay, cool. So yeah, the next thing I want to talk about is this paper, Uncertainty Estimation for Language Reward Models. So first author is Adam Gleave, and you are the second and final author on this paper. So yeah, again, can you summarize what you did in this paper?
Yep. So the goal here was we're doing reward modeling for doing, again, this sort of RL with human preferences task for language models. And the main motivation of having uncertainty modeling is for getting better training data, so active learning. Although in the paper we sort of we mostly focus on just like getting the uncertainty modeling right as an ingredient towards future active learning. And then the paper is like has sort of in some senses is a partial negative result, or sort of found it difficult to beat sort of baselines with the uncertainty modeling we got to. So again, the goal here is human data is precious and expensive. So we want to go ask humans about sort of how a language model is doing on some task, and you only have some budget of times you can ask humans because they're precious and expensive time. So you want to pick carefully what things you ask, and then you train your reward model on that more carefully selected thing, and then you use that reward model for RL in the background.
Okay. So in terms of uncertainty estimation, can you give us a sense of like how hard it is in general, and maybe for people who haven't thought about it much, why should we expect it to be hard? Or should we even expect it to be hard?
So I think in some sense, it is a bit surprising that it's hard, but it turns out to be hard. Like people have thrown their sort of like banged their heads against it in a lot of settings quite a lot. The thing that typically happens is there's a standard thing that works well, namely ensembling, where instead of training one model, you train 3 models or 10 models or something with maybe the same architecture or slightly different architectures. And your uncertainty estimate is just you sort of look at the predictions of all of the models, and then you say, what's the range of those predictions? That's your notion of uncertainty. So that's a very simple method. It has the cost that you have to train n copies of a model, which is prohibitive to do naively with a large language model. So Chinchilla took sort of several TPU months to train, TPU pod months to train. We only have one of them. It has 70 billion parameters. So if you want to do an ensemble with that, you don't have sort of 10 copies of Chinchilla with slightly different weights to ensemble from. So you can approximate it by, say, only changing a small number of the parameters, but the ensembling is not as strong, and so it doesn't work quite as well. So that's ensembling, and that works pretty well, and people use it all the time in production and practical ML settings. And then there are a bunch of fancier techniques, and they just don't work as well often. So it is, I think my prior would be that this is not as hard as it apparently is, but after updating on people constantly failing to beat ensembles, one should have the posterior that is a hard problem.
Sure. And is there much work on, like, in the setting where you have a big model, you only want to retrain some of the weights? Like, is there much known about, like, how much you can leave fixed and still get the benefits of ensembling?
For ensembling, I don't have a good answer for you. We do, so like for the GopherCite paper, for example, we train only, I think that's 20% of the layers. I forget. We often do that. I forget if we did that in that particular paper in the final results. But that's a pretty standard move to make, and it does work well a lot of the time. I don't think I have. So Adam's results were not at that full scale, so I don't have like results numbers for you for like a full scale Gopher Chinchilla run. But I think that, like there'll be some trade off, and the problem is that like that trade off is still like quite expensive. So if for using a tuned language model, we want to sort of fine tune 20% of the parameters of Chinchilla, that's 14 billion parameters, which is 28 gigabytes of bfloat 16 memory, and then you sort of want 10 of them, and that's 200 and like whatever, a lot of gigabytes. That's too much. So I think any slowdown relative to like having one copy of the model is already kind of more than we would want, and then we'd like to get to a point where we can do, without too much extra work, kind of decent uncertainty estimation. And I still feel that is achievable, but it's a hard problem.
Okay. And you mentioned that in this paper, there was some difficulty with getting the reward modeling to work right. Do you think that's just because of the fact that like you don't want to reinitialize a whole model a bunch of times and train it from scratch? Or do you think there are other difficulties?
I don't think I have a great answer for you. There is kind of other work that people are doing in like at DeepMind and elsewhere, kind of multiple different projects on more uncertainty modeling. So partially, I feel like this was kind of one of our first shots at the problem, and I think the problem will be fixed in the fullness of time. We just haven't quite gotten to the answer. As to why it didn't work this time, I think it's often. I don't think I have the full picture of like why we didn't get like further along. One part of it is that, so in uncertainty modeling, there's a distinction between aleatoric and epistemic uncertainty, and I'll unpack those. So aleatoric uncertainty is, if I tell you I'm going to flip a coin, you're roughly 50-50 on whether the coin will come up heads. But you have almost no epistemic uncertainty because you're quite confident that your distribution is correct, and there isn't a way to reduce it further with a practical amount of knowledge. Like if you knew the whole state of the world, you could get it to zero, but you don't. So you're in that situation, you have kind of all aleatoric uncertainty and no epistemic uncertainty. So in that case, like you don't expect to learn more by getting more data about the problem. And in the epistemic case, it's like I flip the coin, it lands, I close my hand, and now I'm going to reveal a data point, what the coin is. And so I'm still 50-50, but I have no aleatoric uncertainty and all epistemic uncertainty. Like I just don't know the answer, but there is definitely an answer to be learned. And so when we want to do active learning, we want to target only the epistemic uncertainty and not the aleatoric uncertainty. So like if you're going to go ask a human a question and it's just a coin flip, whether they give yes or no is the answer, because it's just a purely subjective thing that depends on their mood at a particular time, then you don't want to go ask that question, even if you don't know the answer, because it won't give you any knowledge about the world. Whereas if you learn valuable information that predicts the future, that helps predict the future, then that's the question you want to ask about. And so I think it took us a while for Adam and I to really better understand kind of what the technical definitions should be to separate those two things apart. And I think that part of it was just like, it was sort of our learning experience trying to get into those definitions and understand them. And then there's less time to make the results work.
Okay, fair enough. So in terms of the results, and in terms of things that are sort of confusing to understand, I think a sentence that I took to sort of summarize the results were that the aggregate predictions of the reward model are well calibrated, but the ensemble's estimated epistemic uncertainty is only weakly correlated with model error. And I guess my question is, how can that be right?
Yeah, so again,
doesn't that sound contradictory?
No, the first statement is about total uncertainty, and the second one is about only epistemic uncertainty. So so the goal again is to separate those two apart. And what that sentence is saying is we are calibrated overall, but we failed to do the separation.
Okay. And so I guess, is this just because like there's more aleatoric uncertainty in language reward modeling than other things?
Why does ensembling not work in this domain, whereas it worked in other domains? I think it is a bit confounded by starting with the same model, but I think I'm just not that confident that there are no other reasons driving that, and so I sort of don't have a fully satisfying answer to the question.
All right, and then finally, in terms of the big picture, like where should I see this in terms of your overall kind of language model agenda, if I can say that?
Yeah. So again, like the goal is to improve our ability to collect accurate data from humans, and so if you get this right, sort of two things happen. So one is you can do this active learning step well, where if you have a fixed budget of human data, you can collect more of it effectively, and then get to more accurate classifiers, and therefore catch more safety failures to do a better job. And then the second thing is that even when you deploy a system, you want this machinery running all the time. And so that's for like you build your system, you deploy it, you want it to be constantly thinking to itself, am I confident this is a good, safe answer to the question? And then to do some dodge, either just decline to answer or sort of give some alternative third answer or something if it is unconfident. And so I think uncertainty modeling shows up, I think, in both of those cases, and I think in other cases as well. Just generally, if you want to behave kind of safely in an uncertain environment, it's good to know when you don't know the answer.
Okay.
So we should, by the way, circle back to GopherCite. We haven't said the Pareto frontier result, which is that in GopherCite, so I think I gave the number, say, as 80% on ELA 5 when it tries to answer all the time. If we use the reward model, 67% if you try to answer all the time. If I use the reward model to decline to answer some of the time, that goes to 80%.
Right. 80% out of the times that you answer?
That's right. Out of the times that we answer. This is if you skip a third of the questions. So it stays relatively useful, but it is now significantly more accurate. And generally, like that's with just a pure reward model that doesn't have like a special notion of uncertainty. But the better you are at estimating uncertainty, the better that mechanism will work. And then the more kind of the safer you can be.
Okay. And for that, is it so important to disentangle aleatoric and epistemic uncertainty?
For that, no. Although, so I think it's a bit subtle. The answer is no if you just had to choose now whether to answer or not. But often in a practical situation, you'll have a move where you can gather more data, and then it definitely disentangles. I think it mostly disentangles in a sort of more subtle way, where it looks like a value function, and then you want to do some kind of you want to plan your path through knowledge gathering space to improve your uncertainty. But yes, it will disentangle in sort of subtle ways in the general case.
Okay. The final thing I want to ask is if people have been listening to this podcast and they want to know more or potentially they want to get involved, how should they do that?
Yeah, so I'm on Twitter at Geoffrey Irving. And then there's a variety of papers that I've published recently. So both on the capabilities front, Gopher, and then 2 papers on sort of analyzing risks of language models, sort of alignment of language agents, and ethical and social risks of language models. And then a couple of sort of technical safety papers in language modeling. So red teaming, uncertainty modeling, GopherCite, as we've discussed, and more of those will follow. And sort of those are like, if you follow like DeepMind blog or sort of archive or Twitter, those will show up. But those are the main places.
All right. And if there are talented people who are potentially interested in working with you on these topics, is there some way for them to do that?
Yeah, so I'm hiring for 4 different roles, all working in this sort of space of aligning language models and kind of scalable alignment and explanations. So that's 2 research scientist roles, 1 machine learning and 1 cognitive science, and then research engineers and software engineers. And I can kind of go through those briefly. So research scientists and research engineers for machine learning are relatively explanatory. That's sort of designing these algorithms, training large models, kind of iterating on the whole system. The cognitive science aspect is, again, because this is about humans, and there's a lot of uncertainties about humans and data collection and protocol design that accounts for human details of actual humans. And so I've sort of hired people before that in other roles. I have some collaborators at DeepMind that have that background, but I could definitely use more people that are excited to do this kind of work. And then I think maybe it's worth highlighting the SWE one. So if people are kind of like experienced, like good software engineers, but don't have machine learning backgrounds, but they've done, say, distributed systems or kind of high performance computing, we also just deal with very expensive things. So we made Chinchilla 4 times smaller than Gopher, but it's still, as I mentioned, like 140 gigabytes in memory. So it's split across a bunch of machines. There's complicated software stacks to make that kind of work efficiently and be able to tune them and use them and so on. And I think maintaining and evolving and sort of researching how to do that work well is important, even if you don't have like a machine learning background specifically. So again, the research scientists in machine learning and cognitive science and research engineers and SWEs, and all of those, there's job descriptions for all of those on my pinned Twitter post currently.
And so it might take a while for this episode to get out, and it might take a while for people to listen to it. Is there an expiration date on these offers, or?
It depends on when people otherwise apply. So not a fixed expiration date, no.
Cool. Well, thanks for speaking with me today.
Thank you very much.
And to the listeners, I hope this was a valuable episode. This episode is edited by Jack Garrett. The opening and closing themes are also by Jack Garrett. The financial costs of making this episode are covered by a grant from the Long-Term Future Fund. To read a transcript of this episode, or to learn how to support the podcast, you can visit AXRP.net. Finally, if you have any feedback about this podcast, you can email me at feedback@axrp.net.